In the next three lectures, we're going to go over the basics of parametric curves and surfaces. In this lecture, what I'm going to do is talk about how we start designing cubic curves, and we'll extend that to surfaces. In this lecture, though, we'll talk primarily about the classic types of an interpolating curve and a little bit about the Hermite curve. Then in the next lecture, we're going to focus on the kinds that are used most in computer graphics and in CAD designs, which are the Bezier curves and the splines, principally, again, looking at cubics for both curves and surfaces, but a little bit of an extension to see the generality. And then in the third lecture, we'll talk about how we actually render these kinds of curves and surfaces in WebGL. So there are, to get started, there are four types that I think are important to talk about. The interpolating curve, because that's the one that fits through all the data. The Hermite, where you start using some derivative information. And then the Bezier and the spline, which are much smoother. First, the Bezier is smoother than certainly the interpolating form, but uses the same data. And the spline curve is even smoother than the Bezier curve. And we'll look at the underlying mathematics so we can sort of understand how they perform. Okay, so first thing is this idea that if it's parametric and we're talking about curves first, we have a single parameter u, and that determines some function. If it's cubic, there's going to be four terms in it for the four powers, the 0 through the third power of u. Now, as we said at the end of last time, we said, look, since we're going to do the same thing for x, y, and z, and even w in homogeneous coordinates, let's just use p to signify any one, because the equations we get for any of those coordinates in parametric form are going to have the same form, just different input data. So let's just do it once instead of writing them over and over again, or using the matrix form. So if we use it this way, so p of u is a scalar, which again can be x, y, z, or w. And we have four coefficients determined, C1 through C3, and we have four powers of u, so we have the term u to the 0, which is 1, then we have the u term, the u squared, the u cubed. If we put them each in column matrices, then we can notice this looks like the inner product of the two. It's a column u transpose times, it's a row, excuse me, u transpose times a column. So a 1 by 4 times a 4 by 1 gives you a 1 by 1, which is a scalar. So, or you can switch them and do them the other way. You can take the transpose of C and multiply it by U. So this gives you a nice little matrix form for writing a curve where the parameters are all in that column U, and the constants you need to find that depend on the particular data are in C. Okay, so let's start with the interpolating curve and assume we have 4 points that determine it. We'll call them P0, 1, 2, and 3. And I want to find a cubic polynomial that goes directly through those points. So I need C0, C1, C2, and C3. Well, first thing we got to decide is what values of the parameter u do these data points correspond to? And not having any other information, we may as well assume they're equally spaced. Now remember, last time we agreed that we can always have u go over any range, and I can do that by scaling 0 to 1 up to some u min, and from some u min to some u max. So let's just worry about 0 to 1 here. So we can say, well, obviously p0 then is the value for u equals 0, and p3 is the value for u equal 1. And if I'm going to say they're equally spaced, then this is the value at u equals 1/3, and p2 is the value at u equals 2/3. So if I simply evaluate p of u for those values of u and set them equal to the given data, so p0 is the value for u equals 0, but the only term in the equation is the c0 term, because all the terms u1, u to the first, second, and third power are all 0. if I look at a third, then I get the data point P of 1, and then I get C0 plus C1. 1/3 times C1 plus 1/3 squared times C2, and so on. Likewise, for 2/3, that's where it's going to equal P2, and at 1, it's going to equal, I'm going to have the data value P3, but all the powers of U are 1 there, so it's just the sum of the C's. So I have 4 equations in the 4 unknowns, C0, 1, 2, 3, and 3, given the data points P0, P1, P2, and P3, and I could write that in the standard matrix form and just say that, that this column of P's is given as this matrix A times the column for C. So it's just a standard AX equals B, and I could solve it explicitly for these values. It always has a solution. You can prove that, but to accept that that's true. And here's the inverse matrix, because what I really want is the C's in terms of the P's. And here's the solution. Here's the inverse of that 4 by 4. And now I know the C's are given by this matrix times P. And we call it M sub I, the interpolating matrix, because it's totally determined by the fact that I'm doing interpolation on the data points, and M doesn't depend on the data point. So this is again the point that that equation for P really doesn't matter whether I'm talking about X, Y, Z, or W, because I'm going to have the same matrix. The only difference is going to be the data for X will be different from the data Y and different from the data for Z. So this is the cubic interpolating matrix, and it turns out it's not in general the nicest matrix in the world, even though it always exists. And one thing you can see, those of you who've taken a numerical methods course may have talked about it. Anytime you have a matrix that has large values of opposite signs, it's in danger of being what's called ill-conditioned. Even if this A inverse exists, it tends to give you very bad problems with error buildup, because you're adding and subtracting numbers that are about the same size because of the plus and minuses in these values, like having 13.5 here and minus 13.5 over here. And it gets worse as you go to a higher and higher order. So if I talk about go from a cubic, say, to the 4th power, then I have 5 coefficients, and I get a 5 by 5 interpolating matrix that has even bigger numbers than this one, and so on as I go to higher powers. Okay, but let's just look at this one. So now we've said, well, this only determines the segment going from data point P0 to P3, and we like the fact that it fits through this. Now, what do I do when I have more data? Well, we said we want to connect these segments. So what I'll do is, when I do the next curve segment using the same matrix M, but different data, now I'm going to repeat P3. So it becomes the last point for the first segment, but the first point for the second segment. So I just use P3, P4, P5, P6. Now I have continuity where the two curve segments join, but I don't necessarily have any continuity in the derivatives. In fact, I almost never do. You can see the slope over here is going to be on the right for the dashed curve is going to be different than the slope over here at P3 for the blue curve. Now, one way also to analyze that is to redo this equation. So let's go back to the rewrite this the original equation. So we started writing it as U transpose C, and we said, okay, well, we solved the C. That's the interpolating matrix times the data M. And suppose I just take the U transpose and the M. Now, see, that part is independent of the data, and in fact, it's all polynomials, because what M does is it gives me a row BU transpose, where each term in it is a cubic polynomial, because what the constants in M do is sort of jumble up 1 U squared, and U cubed, and they're called the blending polynomials because each B of U multiplies one data point. So it shows how for a given u the data are blended together. So if you write it out from this form, you get p of u looks like the first blending polynomial times the first data point, and so on for the second data point, third data point, fourth data point. So what are these polynomials? Well, if you multiply u transpose times m, you get these four polynomials that really describe the behavior. And notice what these are correct, because what happens at u equals 0, this will all the other, let's put it this way, u equals 0, b1, b2, b3 have to be 0 because they have a u in front, and therefore this will give me just the data point p0. This will multiply to 1. Then likewise at u equals a third, b0, 2, and 3 have to be 0, so it has to interpolate b1, and so on. So these do interpolate, but if you look at the functions and you just plot the four of them out over 0 to 1, they look like this. b0 has to be 0 in order to force it to be to give you data point p0 at u equals 0. It has to go through 0 at a third. It has to go through 0 at 2/3. It's a solid black line. And it has to go through 0 at 1. So in order to do that, it has to look something like this, and it's 1 at u equals 0. Likewise, b1 has to go through b0 at 0, 1 at a third, 0 at 2/3, and 0 at 1. b2 and b3, you can see, are just reflections of b0 and b1 about a half. And the problem here is that because these curves have these inflections, they're not particularly good. They vary too much to give you really smooth behavior in between the points they interpolate. Another way to look at it, let me come back to this picture. Another way to look at it is here you have this cubic curve, which is fairly smooth, but you want to force it to go through P0, P1, P2, P3, and to do that it has to take some significant bends in between the points that it interpolates, and that's kind of what you see here in this figure with the blending polynomials. And in general, that doesn't lead to very smooth curves, even though they interpolate the data points. Now, what if you want to extend this idea to a surface, a little surface patch? Remember, we said if we go from a curve to a surface, we have two parameters we're going to call u and v, and if it's what's called a bicubic patch, then it's of the form Cij, u to the I, b to the j, where all of these terms have the possible powers of u0, u to the 1 to u squared, u cubed, and likewise v goes through 1, v squared, v cubed. There's 16 coefficients that you have to determine, and you need 16 coefficients. Well, one way to do that is to simply evaluate, say, well, give me 16 points to interpolate. So here's P00 is the first one in this corner. That corresponds to U equals 0, V equals 0. This one, P10, corresponds to U equals a third, V equals 0. And likewise for all these points, P33 corresponds to U equals 1, V equals 1. And I can write out 16 equations and 16 unknowns and solve for the resulting values of the coefficients. But it turns out you can actually do things in a much more clever way and just argue like this, which basically says, well, first you can write it this way. If you define V the way you did U as being a column, which we're going to transpose, which has the components 1v, v squared, v cubed, and C is a 4x4 matrix of the unknown coefficients starting with C00. We're going to number the rows and columns from 0 to 3. And P is an array of the data points that you see over here, P00 up through P33. It turns out if you write this out from that equation I started with, it looks like this. So here's the C. But you can also make the following observation. If you look at U equals a constant, you get this curve on the bottom here that corresponds to U equals 0. That has to interpolate these 4 points. Likewise, for U equals a third, it has to interpolate P10, P11, P12, P13, and you go in the other direction. So V equals 0, you have to interpolate P00, P10, P20, P30. Effectively, what that says is you kind of know that from the behavior of the curves and the derivation for the curves that you can get this result for the surface, and it turns out to just be that P of U and V. See, this is the blending polynomials transposed for the U direction, and here's the blending polynomials for the V direction on the right, and in the middle are the data points. This is in a little more detail in the book, but basically it's saying if you know how to do curves, you know how to do surfaces. Now, if I multiply out everything here and everything over here, I can write this. These are the blending polynomials in U. These are the same blending polynomials in V. And so if I do multiply this all out, each data point, Pij, gets multiplied by the product of two blending polynomials corresponding to I and j, and it looks like this. You get each P of U and V can be written now as a blending polynomial in U, a blending polynomial in V, times a data point. And this is called a little blending patch. It describes a little tiny patch as U and V go from 0 to 1. So we know all the behavior here from the behavior of the interpolating curves, because these are their blending polynomials. And so you have the same kind of result to the surface, that it has to interpolate those 16 points, but it's not particularly smooth as it goes between them. So what can we do about that? Well, we can look at two approaches. One is to use a different kind of data, which we'll do that first, or we can take the same data we used for the interpolating curves and the interpolating patches and use those data in a slightly different way. So let's start with this, that we don't like the fact that we don't have smoothness, and we're worried about discontinuities of the derivatives. For the curves, they're at the joint points. For the surfaces, they're along the whole edges of those little patches. So what we're going to do is use them other than for interpolation. But when we use them for other than interpolation, we still want to be sure that the resulting curve or surface comes close to those points. And we'll define closeness as we go through this in a very specific way. So the way we'll start getting at that is first in a somewhat different way, where we start using derivative data. So this is called a Hermite form. It goes back quite at least probably 150, at least 100 years, probably 150 years. And it says, what if I had different data? What if I said, I have a little segment that a polynomial I'd like to get, and I want it to be cubic, but now I'm going to say that I've given data, I'll assume I have this data, that I have not only the values that interpolates at the endpoints of that segment, but I'll say, forget about the interior points and interpolating them. Suppose I give you the slope at those two ends. So I have the derivative at 0 and the in-term derivative with respect to u, and the derivative at the other end 1. So here I'm just drawing those tangents to the curve, which are based on the derivative, and you can see that the resulting curve is going to be much, much smoother. And what happens when I join that to another segment? Well, when I join it to another segment, I'm going to use the same data at the join point. I'm going to say it has to interpolate P of 1, and it has to have the same derivative on either side. So now I have both continuity at the join point and first derivative continuity at the join point. So this should be a much, much smoother surface, and we can derive the equations exactly as we did before. We can say, if I give you the data, well, the interpolating conditions at the end, there's that P0 is P of u evaluated at u equals 0, which is just C0, and P of 1, which we'll call P3, because that's the same notation we used before, is given as the P of u evaluated for u equals 1, and that's the sum of the C's. And now I'll apply two different conditions. So the derivative of P of u, it's just a polynomial, so I know how to take the derivative. C0 goes away. C1u when I differentiate it gives me C1. C2u squared when I differentiate it gives me 2u C2. And the cubic term gives me 3u squared u cubed. So I can know that derivative. I evaluate it at 0. That gives me just C1, and that must be the data that I assume I'm given, P prime at 0. And likewise at 1, I evaluate this and I get C1 plus 2C2 plus 3C3, and that has to be the final data value that I think that I have. So I can write that out in matrix form, and it looks like this. So once more, I have 4 different data points for now, because I have 2 derivative values here. And I get a matrix times C, simple matrix. When I invert it, I get this matrix I call the Hermite matrix, which you can notice doesn't have as large values as the interpolating matrix. So this should be smoother, and in fact, it's much, much nicer, as you'll see here. Here are the blending polynomials. We do the same thing to get blending polynomials. And these functions, I can plot them out, and they're much, much nicer than the functions I got, the blending polynomials I got for the interpolating form, because they go fairly smoothly through these. Well, see, this has a double. One reason you can see here, look at this one here. See, it's got a double root at 0, and then it has a second root at 2/3, and so it's a much, much smoother function. The problem is that we generally don't have continuity data. We don't have derivatives. We only usually have only data points, which I have to be close to, which we'll call control points. They're points, not derivatives. However, what I'm going to do, I think in the next lecture, is show you how the Hermite form, it's not here for nothing, you can approximate the derivatives here, and you'll wind up with the Bezier form, which is probably the most commonly used one, certainly in computer graphics. Okay, so a couple of things to remark about. First is just very briefly about parametric and geometric continuity. If you're working in parameter space, you essentially get an extra variable to play with, and so if we say you have to make, suppose we're working 3D. I won't worry about W for now. If I say X, Y, and Z have to be continuous and have certain derivatives continuous at the join points, that's called parametric continuity, because each parametric curve has to be continuous or have a second or third derivative continuous. If I worry about the curve in space, where I look at the parametric curve P of u, then if I say obviously continuity is the same, but when I start talking about derivatives, I'm not talking about the derivatives with respect of the x, y, and z curves. I'm really talking about the tangents to the curves agreeing at the end. And it turns out that gives me more flexibility, as we'll see a little of that later. So for example, if I look at this idea of the Hermite curve, you can approximate, and I'm looking at this in space, P of u could look like this, or it can also look like Q of u, where it interpolates the same data. But notice in this case, the tangents at this point are the same. And if I make the tangents longer, so if I start with P of u, let's look at it this way. I start with P of u. I say, well, I interpolate the endpoints, and I have the tangents here. What if I make the tangents longer? Well, there's still the vectors here, longer. They're still tangent to this curve, but it determines a different polynomial Q of u when I use the data for the longer vector here. And essentially, so that gives me a little more flexibility, and it says I can have the same sort of continuity here, but I can have a whole family of curves that look like this, go in the middle here, go even higher up here. And so those issues will be important if you wind up studying this. In terms of graphics, what it essentially is saying is that the continuity is the same, but the velocity is different. This corresponds, if you think of like you're designing a curve for, say, a camera to track along. which is a very common problem. What will happen here is even though you can go along here smoothly and in the same direction, the speed will change on the left and the right. And so this length here is proportional to how fast you're going in that direction. And so often, even though you use this geometric continuity, you may want to worry about parametric continuity because you don't want a speed change in your camera as you go to another segment. But if it's designing a shape, then you sort of like having this extra degree of freedom because sometimes you'll want this curve and sometimes you'll want the Q curve. So finally, for this lecture, and then next lecture we'll get on to Bezier and splines, is just mentioning that these kind of ideas work at higher dimension. And in the old desktop GL, before functions were deprecated, there was support for really any dimension that you wanted to do. But as you go to higher and higher dimensions, the resulting matrix, especially for the interpolating form, become more ill-conditioned. The curves are less smooth, and you can have a lot of problems due to buildup of numerical errors. The alternate idea would be, well, if you use more data points, then perhaps I could use this resulting curve over a longer distance. So I can use, instead of having two segments that go over some distance in space, I could have just one segment. The problem is that generally the extra work that you do and the resulting potential problems in the numerics probably dictate you to more to using cubics. And if you look at what people do, there's just, not in every application, but it's overwhelmingly in favor of using these cubic parametric curves. So next lecture we'll look at the ones that we will be doing a lot more work with.